Here's a typical example of cam and crank correlation where we need to qualify it with a known good. So we suspect there is an issue with this vehicle. It's crankshaft, camshaft and number one injector, which is always a bonus to keep that one in there when doing correlation. And how do we know if this is a good one? Well, we go to the reference waveform library. Remember, you need a username and password for the auto forum, automotive scope connected and an internet connection. And the make in question is a BMW. It is a 3 Series, number of cylinders 4. Notice as we get through the search criteria we're down to 15, and let's try that. Let's just see what comes up, and we'll do this correlation, and we're after, here we go, BMW 3 Series, camshaft sensor, Hall effect, injector current and crankshaft. That's cool. This is a good according to the upload from Pontmot, so thank you very much for that. And we'll pull in reference waveforms, so we'll use these as references in our capture. So we'll have the camshaft, we'll have injector current, and we'll have crankshaft, of course. So it looks a bit messy here to start with. Let's try and separate these. So there's my original, and there's the camshaft. Sorry, there's the camshaft. There's my original injector current, and then we'll pull these down here. And this here, let's try and just minimize or change the scaling by hovering over the scale. I'm using the mouse wheel to do this. This makes life really easy and very, very quick indeed. Alright, so hopefully the first thing that comes to light is we are on different time scales. So this was 20 millisecond divisions, and I think from a previous download that capture was 200 millisecond divisions. So we've got far more data than you can see here, and we can prove that by just going on to the reference waveform and delaying. So here we delay by 50 milliseconds, 60, 70, 80, so on and so forth, and then we double. If that capture on the waveform library was 200 millisecond divisions, we've actually got 2 seconds worth of data to scroll through here. Alright, so what we need to do is get some kind of alignment between what we've downloaded and what's actually in our original capture. And the quickest way to do that is to align, I'm going to align with injector current because that works really well. So we've got that point there and that point there. We've got 98.97. So if I go to the delay option for our reference waveform and I enter in here a negative value because I want to move this waveform to the left, that's negative 98.97, and it's milliseconds, and we'll see straight away there we've got some reasonable alignment with that first event, not with the second event. Why is that? Well, that's because our engines are running at different speeds. So a number of issues to tolerate here. One is the fact that these captures are on a different time scale, and then the engines are running at different speeds. Of course we can prove that if we use the time scale here, time ruler, sorry, and just measure one rotation of the crankshaft. On our original capture is 782 RPM, and now on the downloaded capture from the reference waveform library they are 837 or 832.7. so that is a little bit of an issue, but all in all we can tolerate that. So going back to the delay that we created a delay of 98.97. We must do the same with all waveforms. So we'll go to the reference waveform and we'll delay that as well. 98.97 milliseconds, and that, oh, I never put negative, so that's what happened. Because I haven't put a negative value, the waveform has moved to the right. So let's change all that altogether. So it's negative 98.97 milliseconds. Okay, that's better. So let me just check. 98.97. 98.97, and then finally we do the same with the crankshaft. So that is negative 98.97 milliseconds. So now we see that we're starting to get some form of alignment. Yeah, looking at the start of the capture, I think we're not too far away, but of course they're going to go out of sync again because they're on different speeds. So to get some order here, let's add a scope view. So we'll go to views and we'll add scope view. And if we click on the scope view tab here and just drag this onto the graph view there, we can actually organize these in columns, and I think it'd be a good idea at this point to populate scope view 2 with our items from the reference waveform library. Those are the references, and we'll remove the originals. Likewise, when we click on scope view 1, we can remove the downloaded captures, the reference waveforms, and keep the originals. And let's get a little bit of alignment going. I think we could probably make more use of the graph view here. That's looking pretty good. Let's reduce this just a little bit so we got some kind of symmetry. Again, just hovering over the scale. And now we can bring out our rotation rulers. So rulers now, and we'll go on to phase. And we'll start working with scope view 2, and we'll use that as our reference point there. And then 720 degrees later, the same point, so 360, 720. There we go. And we'll choose a point in which to measure, but prior to that, let's just do exactly the same with this side. So rulers, phase rulers, not graph rulers. Exactly the same from this point here to 720 later. Brilliant. So we're getting some kind of alignment now between the two. And we'll start here on the far left because we know we're running at different engine speeds. So as we move on, we're going to see a change that we'll have to tolerate. But we are really interested in tooth count at this point. And it's probably a good idea to bring these closer in alignment. Right, and let's zoom in on this area here and see what values we've got. So let's go from that first falling edge of the larger pulse after the missing tooth to the first rising edge of our camshaft. And we have 32.78 degrees and a tooth count of 1, 2, 3, 4, 5, 5.5. Alright, let's repeat that now on our capture from the reference waveform library. We've gone from the first rising edge of the missing tooth, after the missing tooth, sorry, which is there. Let's move that out of the way. And we're going to the first, we went to the first falling edge after the missing tooth to the first rising edge of the camshaft thereafter. Okay, and we are on 40.72 now. There's a concern straight away. Right, let me move that away. That's not good. What have we got here? 1, 2, 3, 4, 5, 6. Nearly 7 teeth to that point there, which equates to 40.72. On this side here, 1, 2, 3, 4, 5.5. Okay, so we are what appears to be at least 1 tooth out, maybe more. Maybe there is a little bit of fluctuation or movement in the chain on these vehicles. So yeah, it looks like we have a positive case here for possible chain issue. Ironically, this vehicle here is running fine. This is actually my vehicle, so looks like I've got work to do now. But nevertheless, there is a method in which you can align reference waveforms from the library that are captured on different time bases and also accommodate the difference or the changes in engine speed. Alright, I hope that helps.